Anybody have any questions? Number 28. All right, so sum n equals 0 to infinity, 1 plus sine n over 10 to the n, right? So this is the integral and comparison test section, so you kind of know what you're supposed to do here. I mean, it should be either an integral or a comparison. If you were looking at this, what would your instinct be, or did you have an instinct as far as what you want to compare it to? Did you have anything in mind to compare it to? Okay, so like a geometric series? Okay. Okay. Trying to come up with something to compare it to. What, anyone else have an idea of what they could do here? I mean, you're on the right track. You're seeing geometric series here. No, you don't have to have a geometric series to, you don't have to be looking at a geometric series to compare it to a geometric series. It's anything, any series you want to come up with. So let's stick with your geometric series idea. I'm guessing you wanted to somehow leave it as a 10 to the n on the bottom. And then on the top, here's the part that's a little tricky. If you do this, 1, right, that's a geometric series. That's actually 1/10 to the n, which would be geometric. We would have r as 1/10, which is less than 1. So we'd know that that would be a convergent geometric series. The problem I think you're going to run into is when you actually try and run the comparison. Because for comparison test, if this one converges, if your b sub n converges, which it does, then the inequality we would need to have hold would be what? We need our a sub n's to be less than or equal to b sub n's, right? And you might have a little issue with this inequality. Let's see. If I have my a sub n, which is 1 plus sine n over 10 to the n, is that less than or equal to 1 over 10 to the n? So if you multiply both sides by 10 to the n here, right, you clear it out, and you just have 1 plus sine n is less than or equal to 1. Then you could subtract 1 on both sides. So you get sine n is less than or equal to 0. Is that true? Not always, right? Not always, because sine's going to oscillate back and forth between 1 and -1, right? So that's not always going to hold, right? But this is actually the correct idea. There's just something off a little bit. Take a look at this. This denominator here is, numerator here is 1, right? The numerator here is 1 plus sine. Now, sine always has to be between what two numbers? -1 and 1, right? So the biggest that this could ever be is what? When you add them together, 2, right? 2 is the biggest it could ever be. So why don't we choose a different numerator here that would still make it a geometric series? Make it 2, right? We could try 2. Let's just see what would happen. If we change this to a 2 instead, that's a constant, comes out. So we still have a geometric series with 2 here, and this is still going to converge because r is still 1/10. But this inequality now becomes 2 here, right? This side becomes 2, and now it's 2 minus 1, which is true, right? Sine is always less than or equal to 1. That's a very small adjustment that made it work. But you had to see that that numerator was bounded, and so that you could come up with a better, yeah? Okay. Okay. Yeah, there's no, I mean that's what it's there for. It's there to, you pull that test out whenever you need it. Okay, this make more sense? Now, I mean, you could also have done it with like 4 up here or 10 or something else, but you couldn't use 1. 1 wasn't quite enough. It didn't satisfy this inequality. So at this point, therefore, your conclusion is that your series, right, converges. But again, we don't know what it converges to. All right, I'll talk about one more question if anyone has anything else they want me to discuss on the homework. Wait, what? 30, okay. Uh-huh. See, you had some, it was n plus 5. It was cube root, n to the 7th plus n squared, right? And you said you wanted to compare that to what was your comparison? Okay. P being what, though? What did you figure out that you wanted to use? P to, okay, so it was going to be n to the 1/3. That's what you were going to compare it to, right there. Okay, so this is a good, I'm glad that someone's asking about a problem like this, because there's something kind of what I guess I didn't stress enough in talking with a few of you after class and helping out with some problems. Something I really want to stress. When we're looking at the behavior of a series like this, we want to think about how is the numerator behaving? Like, what is it really acting like? So if n gets really, 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 really big, right? This numerator is really just acting like n. It's not acting like n plus 5, because plus 5 isn't going to matter when it's huge, right? The plus 5 is just insignificant if that number is ginormous, right, for lack of a better word. So the numerator here is behaving like n behaves. And the denominator is n to the 7th plus n squared. This n squared almost acts like the 5 here, because n to the 7th is going to get bigger so much faster than n squared will, that when we're talking about large n, this is almost like a trivial little piece on the side. Does that kind of make sense? So this is like overwhelming the denominator, and then you have cube root of it all. So the denominator is behaving like it's an n to the 7th with the cube root. That's what it's behaving like when it's large, when n is very large. So this gives you a good candidate for your comparison. Now, I'd have to figure out what this is. I'd have to rewrite this as n over n to the 7/3, rewrite it in rational exponent form, and then rewrite that as what? N to the 1 minus 7/3. That would be n to the negative 4/3, which is 1 over n to the 4/3. Now you were going to use 1/3, right? Okay, so n to the 1/3 would diverge, and were you not able to get the inequality to work? That's probably why. So this is what I would use as my candidate for this comparison. Did anyone do this one? Did you do that one? Yes? Yes? Is this what you used? Yes, and it works, right? You think? Not sure, because it's number 30, right? Okay. This should work, but the thing is, I did one just like this in class. I think it was the last one I did in class, actually. Where is it? Yeah, this one right here. See? Oh, wait, I did that one. I actually did that one in class. Well, how about that? P series. Okay, so if you go back, you can look through this, but it's all right. It's all right. I mean, I would rather you work it through and, think through it than just say, oh, yeah, there, he did it. Ha, I can just copy it down. All right, let's get going. We have got a lot of material to cover. We stopped last time. We had done the alternating series test was the last thing that we really discussed, right? And now we're going to move on to some definitions. Okay, the first definition we have is what's called absolute convergence. I get the feeling I did talk about this, but we'll start here. It's a good place. Absolute convergence. Okay, so even when I was a student, I heard absolute convergence. I was thinking of absolute as meaning like this is like the ultimate convergence, like the most powerful convergence. I wasn't thinking of it in terms of what it really is. It just involves absolute values. So pay attention to that. Don't misuse the word absolute like I thought it was. So if you're given a series, I'm just going to write it like this now. We all understand that that's an infinite series, right? Given a series, we say that this series is absolutely convergent if the series, which is comprised of the absolute value of the sequence, converges. So what you do to see if a series is absolutely convergent is you take the series, you take the sequence, the definition A sub n, you take its absolute value, and then you look at that. If that series converges, then you can say that this one up here is absolutely convergent. All right? So let's take an example so you can kind of see how this works. Let's look at the series. We're going to always assume n starts at 1, right, unless I write something else. All right, what type of series is this? Alternating series, right? This is an alternating series. So if I wanted to know if this converged, I would probably use the alternating series test. But I'm asking you right now, is this absolutely, I'm just say abs convergent? Is this absolutely convergent? Well, let's take a look at it. So we go in here, we rewrite this series, but this time we take the absolute value of what was there. And when you take the absolute value of -1, it's just always going to be a positive 1, right? So this is now going to become 1 over n cubed. So I don't need the absolute value. As long as I resolve this -1 will always be a positive 1. And now when you look at that series, that's a P series, right? P series. P is 3, which is greater than 1, which means it converges, right? So since it converges, since the absolute value of A sub n, here's A sub n, the absolute value of that converges, this series up here is called absolutely convergent. All right? So the answer is yes. So when you're looking at whether or not something's absolutely convergent, you look at the absolute values, but your conclusion refers back to this one. This is absolutely convergent, right? This is absolutely convergent. Now, the next natural question would be, well, was it convergent to begin with, right? Not absolutely convergent, but was that even convergent to begin with? Let's see. So converge or diverge? You tell me. So I'm not asking you absolute convergence or divergence. I'm saying convergence or divergence. Okay, how are you going to convince me it's not? It's alternating, yes. How do we check to see if an alternating series is convergent or divergent? Alternating series test, right? We have a test for it. It's on our sheet. Did anybody not get the sheet last time? You need a copy of that? Anyone else? They were free last class. They're $5 today. No, I've got a bunch of them. Sure. Anyone else? I've got a couple copies here. No? Change your mind. They're right there. Okay. So is this one? So alternating series test says, well, we have to have an alternating series, right? And there were two things that we had to have, right? We had to peel off the part of it that we were calling our a sub n. So I'm going to rewrite this. I have the negative 1 to the n times 1 over n cubed. This piece right here was the piece that we refer to as our a sub n in the actual alternating series formula, right? The negative 1 to the n is always going to be just the thing that makes it alternate. We have to identify what's the rest of the series comprised of. It's comprised of the 1 over n cubed, right? So what does the test say? It converges if a sub... The way it's written on here is a little different than I did in my notes. I don't know why all of a sudden I switched to a sub k. The way I did in my notes is I said, we want to show that a sub n is greater than a sub n plus 1, greater than or equal to a sub n plus 1. The formula sheet says a sub k greater than or equal to a sub k plus 1. What is this showing again? What does that inequality show? It's a what kind of sequence? It's a decreasing sequence. So we're just trying to show that this right here is decreasing. I think it might be obvious that it's decreasing. Let's check this. It's 1 over n cubed greater than or equal to 1 over n plus 1 cubed. I'm out of room, but I'll bring this up. Is n plus 1 cubed greater than or equal to n cubed? Is that true? Yeah, I mean, we could go through and actually multiply that out, like expand it and cancel things, and we would come up with something that makes sense. But I think we can all just logically say n plus 1 is bigger than n, so n plus 1 cubed is bigger than n cubed. Right? We okay with this? So it is decreasing? Yeah. The second condition that we have to have hold is what? Limit n goes to infinity of a sub n, which for us is 1 over n cubed. Does that equal 0? Yes. It's 1 over infinity, right? That goes to 0. Therefore, by the alternating series test, the original series, what? Converges. Right? This alternating series converges. So, not only does this, well, let me put it on the next page for you. I'm going to summarize what we know about this series. So, is convergent and absolutely convergent, right? Those are two different things. Okay? To be convergent and absolutely convergent are two different things. If I say it's convergent, That means by itself it's convergent. To say it's absolutely convergent means that when I take the absolute value, what's inside it's convergent. Got it? So I wonder, maybe this is actually going to become a theorem. What do you think? This is a question for you. Could this possibly become a theorem for us? Theorem. If it's convergent, then it must be absolutely convergent. Y'all okay with all my abbreviations? What do you think? If it's convergent, do you think it then has to be absolutely convergent? You're shaking your head no. What? No? Can you give me an example of something that would not do this? Like harmonic type thing? If it's absolutely convergent, you think it would have to be? No? Okay. You think it works this way? Okay. So we have different ideas here. Well, okay, so this is a great opportunity for us to think about the way logic kind of works, right? If you're trying to prove a theorem is true, you have to prove it's always true, right? If you want to disprove a theorem, well, if it's a theorem, really it's already been proven, but a conjecture, right? If I have some statement that I think is true and that it's always true, the best way to, I guess, convince myself that it's always going to be true is to try and find counterexamples. Okay, so I might think that this is true, but if I can find one example where it's not, then I can throw this out the window, right? So let me see if I can come up with something that is convergent by itself, but is not absolutely convergent. So check out this one. As an example, take -1 to the n over n. Is that convergent? Well, it's an alternating series, right? It's alternating series, so let me rewrite it like this. What I'm doing is what I will standard and what you should do every time you see an alternating series is separate the negative alternating part from the rest of it. That rest of it is your a sub n. So I'm going to focus all my attention on this 1 over n, and I'm going to run the alternating series test on that. I need two conditions to hold, right? I need to be decreasing, and I need the limit as n goes to infinity of that to go to 0. Are those both going to hold? First condition is a sub n greater than or equal to a sub n plus 1. Well, is 1 over n greater than or equal to 1 over n plus 1? Multiply through n plus 1 greater than or equal to n. I'm hoping after doing enough homework you're comfortable with me doing this step. Is that true? Yes, 1 is greater than 0, that's true. First condition is going to hold. What about the next condition? I need the limit as n goes to infinity of 1 over n to go to 0. Is that going to be true? Yes. So this is what? Therefore, by the alternating series test, this series, -1 to the n over n, is convergent, right? It is convergent. Now, is it absolutely convergent? So how do we check the absolute convergence? Take the absolute value. So I'll put but, right? The sum of the absolute value of that series, or the sequence inside, is just 1 over n, isn't it? That's just 1 over n. And that's harmonic, right? It's harmonic series. A p series with p being 1, right? That's what that is. What happens to the harmonic series? Diverges. Yes. No. Say one or the other, though. Don't just be like 1 over n diverges. So, I mean, we have a final conclusion here. We can talk about this series. Therefore, the series -1 to the n over n is convergent, right? I'll be less lazy here. Is convergent, but not absolutely convergent. Which means, what about that little theorem I thought I might have up there? No, it's not going to happen, right? As soon as you come up with one example where something like this isn't true, it can't be a theorem. So it's not possible. Now, we said maybe the other way would work. What if it's absolutely convergent? Do you think that that means that it would have to be convergent? I see some shaking of heads. Let's see here. Let's try that theorem the other way. Question mark. If a series is absolutely convergent, then the series by itself is convergent. Another way you could have written that is, instead of writing this, you could have written this, right? Because that's really what it means to be absolutely convergent. It means that that little piece there with the absolute value converges. I should put here converges. So I'm gonna actually show you this is true, but I'm not going to give you, I can't give you an example to show you it's true, right? Because just because it holds one time doesn't mean that it's always going to hold, right? I could disprove it by showing you one example, but I can't prove it by showing one example. So I'm going to do it just kind of logically. Think about it. So we're assuming that when we take a series, let's say series A, the absolute value A sub n, right, like this. What this looks like is the absolute value A1 plus absolute value A2 plus absolute value of A3 plus, right, forever and ever. And this, we're saying, converges. Right? That's what we're given in the problem. In the theorem, we are assuming that this is true. So I'll put above this. We are given that when we look at the absolute value of each of the terms and add them up forever, we get a number, right? It converges to a number. It's a finite value. Now compare that to this one. Look at this with no absolute value. It's just A1 plus A2 plus A3, right? Plus forever. How do I know that's got to converge too? We're adding these up, right? If A1 is positive, isn't it the same as this? Right? So if this term right here is positive, then these are the same things. If this term is positive, they're the same things. But what if this A3 is negative and that one's positive, right? If that one's negative, does that do anything? No? What is it going to do? This sum will be less than that sum, right? That's basically the idea here, is that this sum will be less than that one. And if this one's finite and this one's less, then it should be below it, so it should be finite also, right? Does that kind of make sense? So that's the argument I can make for it, but it's an actual theorem. This would not be considered a proof, but it's just to kind of give you an idea that the theorem is true. So we have that this theorem is going to hold. So if you have absolute convergence, that implies convergence. All right? I have a couple of more examples here, actually. Oh, I think that's good. I think we're ready to move on to the next test. Ratio test. The ratio test, I'm going to put a star next to it, is one of the most useful tests we have. All right? We're going to use it a lot in the next few sections. So here's what the ratio test says. Oh, and no, I don't have that to hand out. Never mind. Given, this is on your sheet, right? Ratio test, right? So you're given a series. It says if there's three things. If, well, two things, sorry. If the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is equal to L, which is less than 1, then the series converges. The great thing about this test, and I'll point this out as we move ahead, this test does not care if you're an alternating series or not. You can use this on a series that's not alternating or alternating, and because you're going to take an absolute value, it won't matter. All right? So what you're doing, though, look at what the test is doing, the ratio test. Ratio of two things. What two things is it the ratio of? The n plus 1 term divided by the n term. So it's, you have all these terms of the sequence, and you're taking the next one, right, the n plus 1, you're dividing that by the one before it. And you're hoping that the ratio of those is less than 1. All right? It's converging to a number less than 1. If that happens, the series converges. Now, if that same limit, oh, also, hold on. I need to add something in here. Then a sub n converges, and not only does it converge, it's absolutely. This is a pretty strong condition, I guess, because we're saying if that ratio is a finite number less than 1, then not only is this series convergent, it's absolutely convergent. Remember, absolute convergence implies convergence, right? If it's absolutely convergent, that means it had to be convergent. So this is saying that it's very strong, gives us both conditions are held. Now, if that limit turns out to be a number greater than 1, or infinity, then it diverges. It's written a little bit different in your sheet here, but just those are the two things that I have. And let me see if there's a third. I do have a third that's not on your sheet. What if the ratio test gives you a 1? Because that hasn't been looked at, right? If your ratio test gives you a number less than 1, it converges. If it's greater than 1, it diverges. But what if it is 1? Does it say it on there at all? Yeah, okay, it does say it over there in the notes. If it equals 1, test fails, which means the test doesn't tell you anything. So we really hope to not get that to happen. All right, let's see. What else does it say about this test over here on the side here? Useful if a sub n involves factorials or nth powers. Keep that in mind. That's what the little comments say over here. If you ever have factorials or nth powers, this is a useful test. All right, first example of ratio test. Let's find some n equals 1 to infinity of -1 to the n times n squared over 4 to the n. Okay, now, could I use alternating series test? Yes, I could, right? I could. The only thing I don't really care about with the alternating series test is possibly doing that inequality. You know, the inequality I have to show, it's decreasing. I might be a little bit skeptical on that. But let's just see how the ratio test works here, because you've got to get real comfortable with this test. Ratio test. Now, I'm motivated to use ratio test because I see a power, nth power. I see that there, so I am going to start thinking ratio. So I need to set up a limit here. Limit, n goes to infinity. All right, a sub n plus 1. What is a sub n plus 1? Well, this whole thing, all right, this whole thing is my a sub n. The whole thing. Because I'm not doing the alternating series test, where I have to separate the a sub n from the alternating part. I'm looking at the whole thing as my a sub n. What do I get when I plug n plus 1 in for everything here? Well, -1 to the n plus 1, right? Times, now this n squared becomes what? N plus 1 squared, right? All over 4 to the n plus 1, right? And that's a sub n plus 1. I need to divide that by a sub n, which is -1 to the n times n squared all over 4 to the n. I've got big absolute value outside the whole thing, right? All right. Now that may look like a big mess right now, but it's going to actually turn out to be a really good thing, all right? First of all, the -1s. They're not going to matter, are they? Because at the end of it all, I'm going to take an absolute value. So the absolute value of -1 right here isn't going to matter, and the absolute value of -1 right here is not going to matter. It's all going to they're all going to turn into 1s, so I can just get rid of them. All right, now I have a fraction divided by another fraction, right? Anytime you have a fraction divided by a fraction, you can basically flip the second fraction up and do like a multiplication of the reciprocal. That's what we will do every single time we do ratio test. So from here on out, I will not write a sub n plus 1 over a sub n anymore. I'll write a sub n plus 1, and then I'll write the other one, but already flipped. You'll see when I do it from here on out. Just realize, though, that if you were to follow the formula, this is exactly the way you would write it that first time. Then you would wind up flipping it. Okay, so here we go. I'm going to flip this up. I'm still going to write limit, and goes to infinity. I technically do not need the absolute value anymore because everything that's still in here is guaranteed to be positive, right? But I'm going to keep it because of where we're headed in the next few sections. Just keep it here. I don't want you to start dropping it and then forgetting about it later when you really do need it. Okay, so I said I was going to leave this fraction n plus 1 squared over what? 4n plus 1? 4 to the n plus 1. Whoa, 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 whoa. What was that? What happened? I broke it up, all right? This is 4 to the n times 4 is 4 to the n plus 1. We did that back with geometric series, didn't we? You'll be doing a lot of this with the ratio test, right? That's me just rewriting that right there, right? This piece right here is just 4 to the n plus 1. Everything else flipped. Pardon? That is 4 to the n plus 1. Right, so I separated it out. I'm doing 4 to the n plus 1 equals 4 to the n times 4 to the 1, right? And so I don't need the 1 on the 4, so I just write it like that. Right? That's what that is. Everyone? Yes? Okay, okay, all right. All right, so what cancels here? 4 to the n, that's it, right? That's all that cancels. So I think if you look at this here, I could, if I wanted to, maybe, how about I expand out that numerator? What's n plus 1 squared? Well, n squared plus 2n plus 1, right? And the only thing left on the bottom is what? 4n squared. And now if I take this limit, I get infinity over infinity, so I can apply L'Hopital's rule, right? L'Hopital on this once would give me what? 2n over 8n? 2n plus 2 over 8n. I need a new page. Can I proceed, or you want a second to copy that down? So I have, by L'Hopital's rule, limit, we said 2n plus 2 over 8n, right? L'Hopital again, 2/8, which is 1/4, right? That equals 1/4 because n no longer has any bearing on this value, right? This is just 1/4, and that value is less than 1, right? Which means that series converges. In fact, it converges absolutely, according to the ratio test. Next one. I really like this problem. How about this? All right, so let's talk about this, because I think we've kind of gotten ourselves to a point where we need to start considering, when you come to the exam questions, like, you're not going to know what method, right? So let's get just back to like a beginning point, right? Like, what's the first thing we always try for something? N-term test, right? You just look at the sequence inside the series here, and you say, what happens as n goes to infinity? What's n factorial? Well, what happens to n factorial as n goes to infinity? Gets huge, right? So that's infinity on top. N to the n. Infinity to the infinity gets huge, right? So you have infinity over infinity. But you can't use L'Hopital's rule because you cannot take the derivative of a factorial. Doesn't make sense. You could take the derivative of this, but that requires like a logarithmic differentiation, and that would be something you'd have to do over here on the side. It's just not something I really want to mess with. But what I can tell you right now is I don't know if I don't know what the n-term test would tell me. And I don't feel like working for it to try and figure it out, because it's probably going to tell me it goes to 0, which is going to tell me nothing, right? So let me start thinking about other things. It's not geometric, right? You do have a power n, but the base is not a number, right? You don't have like 4 to the n. It's n to the n. We've never had that before. P series? Well, it's almost n to the p, except p here is n, so it's not a p series, right? It's not a fixed power. Integral test. You can't integrate n factorial. You can't turn this into a function to integrate it, so it's not going to work. Comparison test. What do you want to compare it to? You see what I'm saying? Like, there's not a P series we can compare it to. It's not a geometric series we can compare it to. We'll probably be stuck. It's not an alternating series. Yeah. So, but it has roots. I'm sorry, not roots. It has powers of n, right? And factorials. In the ratio test says that you should probably be looking at that test when you see factorials and powers of n. In fact, they're mixed together. So this is like, they're like two big bright lights shining in your face saying, use the ratio test. So let's try it. I'm going to set up the limit as n goes to infinity of the absolute value of, all right, a sub n plus 1. So plug n plus 1 into the whole thing. Get n plus 1 factorial over n plus 1 to the n plus 1, right? And then I'm supposed to come through and divide that by a sub n, which is the same as multiplying by the reciprocal of a sub n. So what should I put over here? What's the reciprocal of a sub n? N to the n over n factorial. Do y'all see that? That will happen every single time you do the ratio test. So why write it as a complex fraction to start if you can just write it like this to start? See what I'm saying? Okay, now because there's powers and things like that, things should start to, cancel out. We just got to massage this thing appropriately. Limit n goes to infinity. That's kind of loud over there, huh? Should we just be rude and just knock back? That's what we'll do. Let's see if they get the point. Or they probably can't. It's all right. Okay, n plus 1 factorial. N plus 1 to the n. Now, we just did this a second ago, right? We had 4 to the n plus 1. We broke it up as 4 to the n times 4, right? So how would this break up on the bottom here? It'd be n plus 1 to the n times n plus 1 to the first power, which I'm just going to write as n plus 1. Y'all agree? Same base, n and then 1 up there. Now that's going to be great. I think they heard us. I'm going to leave the other two alone. It's usually the a to the n, a sub n plus 1 is the one that you break apart, and it starts canceling with stuff over here, right? How about over here? N factorial. Do you remember that we could write that as n plus 1 times n minus 1 and keep going down? But we could also write it like this. We could peel 1 off. You go back and look at when we talked about factorials. If you have a factorial, n plus 1 factorial, you can peel the first factor off, and then the rest of the way down just represent it as a factorial. I think we get cancellation here, don't we? This and this. Pardon? Yes. Oh, I didn't. Yes. That was the whole point of that. Yes. You with me? All right, let's see what's left in here. We have n to the n, right, over n plus 1 to the n. Is this not the same as limit n goes to infinity of n over n plus 1 to the n? And what happens here? N goes to infinity. We have infinity over infinity, which we don't know what that, well, we can figure out what that does, right? Where does this head? Just this inside here. Infinity over infinity. Do L'Hopital on that real quick right here. Let's get 1 over 1. This just goes to 1, right? But 1 to the infinity. 1 to the infinity is an indeterminate form. See, because it's not exactly 1, right? This is not exactly 1. 1 to any power is 1. But this is approaching 1. It's not ever getting there. So this is a little troubling for us, right? Do y'all understand? This is a little bit not a good thing. So what I'm going to need to do is kind of stop the problem, not stop problem, but just really just look at this limit and investigate it. I'm going to drop the absolute value because we don't need it because n is going to be positive always. And now what I'm going to utilize here is something that you learned maybe back when you were doing the section on L'Hopital's rule in indeterminate forms and how to calculate limits like this. So I'm just going to come in here. I'm going to call this limit y. I could have called it anything except n. And then I'm going to take natural log on both sides. Now, the reason why I'm going to compose both sides of this equation with natural log and pass the natural log through the limit, why am I doing this? Why do you think I'm going to do this with the natural log? Because I'll be able to take the n out there, right? And I'll be able to drop it in front of the natural log, which is a property of logs. So that's why I had to introduce the log on both sides. You got it? So I bring in, got natural log y equals limit n goes to infinity. Now it's n times natural log of n over n plus 1. If I look at this, as n goes to infinity, I get infinity times, now what did we say n over n plus 1 is going to? 1, natural log of 1 is 0. So now I have a different indeterminate form. This indeterminate form is infinity times 0. Remember, this one up here was 1 to the infinity. Both of those are indeterminate forms. You can't tell me what's happening. But anytime we have that form, we always try and make it look like this form so that I can do the next step, which is to make it look like an infinity over infinity or 0 over 0. Okay, so now I go to my next line, which will be natural log y equals limit n goes to infinity. So here's what I'm going to do. I'm going to leave the natural log of n over n plus 1 up here. But remember that n that was out front? I'm going to drop it to the bottom as a 1 over n. That's the same as having an n up top, right? Now, why do I do it that way? Well, now take the limit, let n go to infinity. It's going to be a 1. Natural log of 1 is, that's going to 0 over, now 1 over n is going to go to 0. So now you can apply L'Hopital's rule. But you have to apply it to the top, right, and the bottom separately, right? Take derivative of top and bottom. So let's apply L'Hopital one time. My goodness, huh? Okay, if I apply L'Hopital, what is the derivative of natural log of something? Well, 1 over, that's something, right? Now that would have reciprocated back up, but I'm just going to leave it like this. Times the derivative of what's inside, which is a little quotient rule, which will be derivative of the top, n, times the bottom, minus derivative of the bottom, which is 1, times the top, all over the bottom, squared. Now that's all over what? The derivative of the bottom, which is another quotient rule, or you could do a power rule, negative 1 over n squared. You're just looking at 1 over n as n to the negative 1, and then taking the derivative. And as bad as this looks, I'm hoping, because I kind of made this problem up. not made it up, but I just adapted a problem that I had done before on another class. Let me see. This piece here, 1 over n plus 1, just flips and becomes n plus 1 over n. And then over here, this, what does this turn out to be? 1 over, so it's positive 1 over n plus 1 squared, and then all this over negative 1 over n squared. Can I just bring that up? Is that all right if I just flip it and bring it up here like this? So I rewrote this as this, I rewrote this as this, and then I brought this one and flipped it up. What happens here? Limit n goes to infinity. Do we get an n's to cancel? Okay, I get one n here to cancel with one of them there. So what is my numerator? Distribute that n through. N squared plus n? Yeah? Okay. And then what's my denominator? Negative n plus 1. Okay, you want to distribute it now or no? Well, negative n plus 1 squared. Yes? My goodness. Now, I want to expand the bottom out because I want to do L'Hopital again, because this is infinity over infinity again. So we have limit n goes to infinity, n squared plus n over negative n squared minus 2n minus 1. What does that give me? I do L'Hopital on that twice. Or divide through by n squared on all of the terms. What do I get? Negative, yeah, 1 over negative 1. So negative 1? Negative 1? We okay with that? Yes? Okay, so I have natural log y equals negative 1. Now, I wanted to know what y was, not natural log y. So what do I do now? Take e on both sides. So e to the natural log y equals e to the negative 1. So you get, finally, y equals e to the negative 1, which is 1 over e. Okay, so what? What does that mean? It's less than 1, right? This is less than 1. And what does that mean? Therefore, by the ratio test, says that n factorial over n to the n converges. This is a good illustration of how there's really not much that's off the table when it comes to trying to figure out a problem like this. You're back to limits now, is what you've come back to limits, and you're going to rely on your ability to compute limits to be able to figure out these convergence or divergence. Now, they won't always be this bad, trust me. A lot of times they'll just be right away, you know, but they can be. I like this series because when you look at this sum, n factorial over n to the n, just write out the first few of these just to get an idea of what they look like. This is plug in 1, you get 1 over 1, plus plug in 2 is 2 factorial is 2 times 1, but then you have what? 2 to the 2? Isn't 2 to the 2 this? Isn't that 2 to the 2? Okay, and then you get plus 3 times 2 times 1, but then what? 3 to the 3? So 3 times 3 times 3. And then you have 4 times 3 times 2 times 1. That's 4 factorial, but then 4 to the 4 is 4 times 4 times 4 times 4, right? So do you see that the n factorial gets big very fast, right? I mean, n factorial grows quickly, but n to the n grows extremely fast. In fact, I would be hard pressed to find any function that would make sense in this class that grows faster than n to the n. Because it's a combination of an exponential function with like a power function. You have your base and your exponent both growing at the same time. Instead of exponential functions, your base stays the same, your exponent gets big. And we know those blow up fast, right? But now you're adding the element of you're letting the base get bigger too. So they're pretty impressive graphs. All right. So can you see that these are getting smaller and smaller, right? Each of these getting smaller, the ratio. And so because they're getting smaller, the question is, are they getting smaller fast enough? And it turns out they are, because this thing converges. So they are going to zero fast enough to create convergence. All right. The last test, you'll have plenty of practice with ratio tests, trust me. The last test we have is the root test. The root test, not used as much as ratio test, but you have to know it's there. And these are on your sheet, right? Root test. So I think I will not write this all down, okay? Since it's right here and this is our last one, you've kind of seen what I'm doing. It says if you take a series and you take the nth root of the absolute value of the sequence and you get some answer L or infinity, it converges absolutely if L is less than 1. So it's very much like the ratio test. And it diverges if L is greater than 1 or infinity. So it's almost the exact thing as ratio test, except instead of doing a ratio, you're doing an nth root of the absolute value of the series. Now, when does it say it's useful to use the root test? When you have nth powers. Well, we just had an nth power, didn't we? Well, let's try this example. Well, I wonder if that last one would have gone with the root test. No, because that numerator, see, look, the bottom is raised to the n, right? But the top's not raised to the n. So this wouldn't be ideal. Let me show you an example of one that requires the root test, and you'll kind of see it's obvious when you'd use this. If I have 5n plus 1 over 11n minus 1, all of this raised to the n. You see the nth power on the outside? All of a sudden, I'm thinking root test, because the root test is going to tell me that I can come in here and take the nth root of this, right? And the nth root of something to the n's are going to cancel, and then you're just going to be really looking at what the inside is. So by the root test, I need to take the limit as n goes to infinity of the nth root of the absolute value of this, which you don't need to put the absolute value because everything in there is positive, right? This should all be positive. So I'm doing the nth root of 5n plus 1 over 11n minus 1 to the n. So the nth root and the n cancel out. You get limit n goes to infinity of 5n plus 1 over 11n minus 1. Now let n go to infinity, and you just get what? 5/11, which is less than 1. Therefore, this series converges, right? It converges. Yes. You don't need to. You can. The reason why I wouldn't write absolutely here is because if you took the absolute value of this, it would be the same series, right? So if it would be an alternating series, then maybe you would want to put converges absolutely. I won't take off if you don't put absolutely after you do ratio or root. All right, that's it for this section. We're done with tests. All right. What had I assigned there? I done which one? Oh, so I didn't give anything off 463 yet? Okay. Well, here's the 463 assignment. Three through 11 odds. 9 and 11. Oh wait, sorry. On 9 and 11. Just show convergence. And then 19 through 39 odd. Okay, so on number 9 and 11, I say just show convergence because there's part of this section I did not cover is that when we determine a series is convergent, there is a formula that we can use to compute like an error. So we can find the sum within some error. I just didn't cover that. It takes a little bit of time, and I wanted to get through the test. So ignore when it says, how many terms of the series do we need in order to find the sum to the indicated accuracy? So it's like when you keep adding more terms, you get closer and closer and closer. It says, use this formula to determine how many terms you would need to be within a certain tolerance. It's something that you could pick up later on in a computer science class. It would be easy to look at the formula and just apply it. But in here, not too interested in that. It's just, let's do the test. Let's see if it converges or diverges and be done. All right, we're going to start 8.5. I have a handout for 8.5. It's just so you don't have to write all this stuff down. If there's extras, just leave them on the table. I'll get them when I leave. All right. So power series. We finally have gotten to power series. And the first statement I have here is just something that, so we're all clear on something before we move ahead. If someone ever says the absolute value of a number or an absolute value of x is less than c, where c is a constant, then what this really turns into is the statement x must be less than c or greater than or equal to negative c. And I give you an example there. When you say the absolute value of x is less than 2, what you mean is that x is between negative 2 and positive 2. So like on a number line, I say this. What I mean is your x's would have to be somewhere in here, right? In between negative 2 and 2. So if I pick an x here, the distance between x and the origin is less than 2. And so I can move to the right of the origin or to the left of the origin, and the distance from x to the origin would be less than or equal or less than 2. All right? Not including the endpoints here, right? Not including negative 2 and positive 2, because my inequality was not a strict inequality. Or it is a strict inequality. All right, we'll use that later. So now the definition of a power series. And I just didn't want you to have to write all that down and try and just copy me. I mean, I can write it down pretty quickly. A power series is something that we've seen before. It's a summation, c sub n x to the n. So what's different here is the c sub n is like what we've been studying. It's like our a sub n, all right? But they use c sub n because they want you to understand that the c is like constant. Okay, so this is just going to turn out to be a number. This will always be x to a power. And that power will be controlled by the index. If you write out the terms of this, it's c sub 1 x to the 1, c sub 2 x to the 2 plus, and you keep going, right? That's if you started at 1, right? That's what it would look like if I started this series at 1. But how is it defined here? Where am I starting it? 0. So this is different for us. We said a long time ago we could start at 1, we could start at 2, we could start at 0. We just don't start at like -2 or something like that. So for power series, we like to always start our power series at 0 to infinity, c sub n x to the n. And the difference here between that one and the one above it is what? What's my first one going to be? C0, x to the 0, but x to the 0 is 1. So then you have C0, then C1, x plus C2, x squared. And so do you see where the name power series comes from? It's a series of powers of x, right? With each term having some constant there. Also, if we define this, I say here, oh wait, let me get back up, I skipped. So the x here is just something we don't know what it is, and the c sub 0, c sub 1, I say c sub k, those are all just constants, right? If we fix an x value, right, so now if I come in here and I say, let's just let x be 2, then these will all be numbers, won't they? Not only will the c's be numbers, but the x's will be numbers also. And that means it'll be a series, like we've been studying, and therefore it's going to converge or diverge if I fix a value of x, yes? If I leave x as a variable, then you can't tell me really what's going to happen to this, because changing x is going to change the problem completely. Does that make sense? In order for you to talk about convergence or divergence, you need to know what x is. So if I define this to be a function, I define this series here, this power series, to be a function, then this is a well-defined function. If you give me a value of x, right? If you give me a certain value of x, I should be able to look over here and determine about, convergence and divergence. If you give me an x that makes it converge, I'm happy, right? If you give me an x that makes it diverge, I'm not happy. All right, so if we define a function this way, then the domain of this function are all the values of x that would make that converge. Does that kind of make sense? I'm getting glared looks here. Come on, y'all got to talk to me. I was watching this video last night I found online of this guy who's teaching about the same subject. And he is awesome. I mean, I just loved him. It actually humbled me. I was like, wow, that guy is really good. But I noticed something that was so different. He was engaging the class. Every time he asked a question, they were responding. Everyone was responding. Everyone was, boom, here. I mean, he was just like talking to the class. It was great. Every one of my classes, I try and get people to talk to me. I cannot get people to talk to me. All right? You have to say if it doesn't make sense. You have to let me know. If not, the steamroller keeps going, So let me back up and ask again. All right? This power series, we don't know what it does until someone tells us what x is. If x is a number in here, then it's a series and we use our test and we can figure out what it is. Possibly, right? Okay. Once someone gives us an x, it's either going to converge or diverge once someone gives me an x. So what I'm going to do is I'm going to define a function from this power series. And what I'm going to say is that the function is well defined as long as you give me an x that makes it converge. The function won't be defined if you give me an x that makes it diverge. Okay? So the domain of this function are all the x's that make it converge. Does that make sense? Okay. Does that make more sense than it did the first time? Why? I said the exact same thing. Okay. All right. So now, I was saying there, if x is a value for which it converges, then the function is a well-defined function. That's what I'm saying here. The values of x for which the series converges is domain. F is the infinite sum of powers of x. In other words, this is called an infinite polynomial. Right? That's an infinite polynomial right there. All right, so we're going to look at an example now. I want to look at the example where we let all our c sub k's be 1. All of them. Right? So remember I said those c's in front of each power can be different numbers? We're just going to let them all be 1s and just see what we get. So our sum's going to look like sum n equals 0 to infinity of 1 times x to the n. Right? Because what I'm doing is I'm replacing every c with a 1. And so this just becomes, plug in 0 first, x to the 0 is 1, plus, now plug in 1, x plus x squared plus blah, 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 forever, right? Maybe I'll throw a couple more. Well, you have them here. And what do I say here? This looks a lot like a geometric series. Because remember, geometric series look like this. It was sum n equals 1 to infinity of a r to the n minus 1, right? That's what a geometric looked like. But if we wrote out the actual terms, like if we actually wrote them out, it looked like when you plug in n was 1, we got a, then we got ar, then we got ar squared, then ar cubed, forever, right? So doesn't this look a lot like this? Replace the a's with 1. If a was 1, and you replace the r's with x's. If I replace a's with 1s and r's with x's, then that would be the geometric series, wouldn't it? No, not in this case, because they create the same series. Now, look, I will point this out, though, because we will have to address things like this later. My index starting here at 1 is different than starting at 0, but notice that my power here is different than my power up there. Like this one's n minus 1, that one's, so it's been shifted over to compensate for that one. Good question. Okay, so we all see that this looks like a geometric series. So therefore, we know geometric series converge if what? If the absolute value of r is less than 1. So that means this series should converge if what? The absolute value of x is less than 1, because the x is like the r, right? Do I say that on the next page? Yeah, I say it. Thus, this right here, I'm going to just write it up there with this. Converges if the absolute value of x is less than 1. All I'm doing with this example is showing you how a specific series, power series, could be looked at as a geometric series. But this is just one tiny example, right? Not every power series is going to turn into a geometric series. Just that particular one does, all right? So there's a little bit of a connection here, meaning in the sense that we knew when this converged, and this power series, we now know when it converges, right? So the idea of if I define this as a function, you can tell me the domain of this function would be as long as you let the absolute value of x be less than 1. That's the domain. So the domain would be everything between like -1 and 1. You try and go outside of that, this function isn't defined. Right? Okay. I want to look at the next thing. It says general power series. So what happens is this. We use these power series to approximate functions. I believe I showed you this in the past. What we're going to try and get to here. Let me bring this back up. I had it up just earlier today, so it should go pretty quick. Let me see. That's not the one. Oh man, where did it go? I'm just waiting for this thing to load there. Do you all remember a long time ago I showed you this? Where the very beginning of this chapter, in fact, it was so long ago, where I said, hey, we have a function here. Forget the vertical asymptote right here. We have this weird function. I'm going to approximate it with a line. Is that a good approximation? Everyone's like, no. And I said, what if I approximate it with that? Is that better? Everyone's like, yeah, that's better. And I said, what if that, and then this, and then that? And remember this? Very beginning. And so what I did was try to convince you there's a way of approximating that function with a power series, right? Well, what we're gonna find out is that, see, what about over here? Like this was really good right here, right? This approximation, all these dotted ones are an approximation of what's happening around this place, right? But that's a really shitty approximation of what's happening over here. So what a lot of times what we need to do is we need to shift our power series over and move it, all right, so that it's a better approximation near somewhere we're interested in. And so the general power series formula adds into the formula just one little thing, the minus a. You see the minus a next to the x? What that allows you to do, just like in college algebra and pre-cal, subtracting a number inside of a function has a left and right shifting effect, right? So it allows me to move my power series left and right to put it in the place I want to approximate, all right? So that's a more general formula. But it all turns out to be pretty much the same thing. So the general format looks like this. C sub n, x minus a to the n. You have that written down there. And we call this the power series about a. About a. So it's like, where's your series, but where's your power series? It's this power series about a, close to a. Now, if a is 0, right, then that's the first formula I gave you. So that's the power series about 0, the formula before this. Okay? Now, let's look at some things here. If this is a general power series right here, let's take a look at some possibilities here. What if I actually let x be equal to a? What would happen to this power series? What would it become? It becomes 0, right? Every single term would be 0. 0 to the n, 0 to the n, 0 to, right? It would just be 0 the whole time. So if that's 0 and I say add those up forever, that would converge, right? It would converge to 0. So if x equals a, this sum, a minus a, can I just put 0? Therefore, it converges. I mean, it converges to a trivial place, right? It adds up to nothing, but that's better than it adding up to infinity, which would mean diverge. So if x is a, this thing converges. What if x is not a? Well, it says here what? If x is an a, I've got to figure out what's happening. I have to actually go manually figure out what this series does. And that's what we're interested in. We know if x is a, we know what's going to happen. But if x is not a, we investigate. So I think it's time for our first true example now. That's just to kind of motivate the idea. Here's our example. I would like for us to find what values of x I should say for what values of x? For what values of x does sum n equals 0 to infinity of 2n plus 1 x to the n over n factorial converge? I want to see if anyone has caught on to this at all. If I were to come in here and define this function as a function, f of x, what's another way you could restate this question of what I'm asking you to do? I think you're going beyond. You're looking at what's in there. I'm just saying in terms of the big question here, I'm asking you for what values of x does this power series converge? But if I look at the power series as a function, then what am I asking you in terms of that function? For the domain, right? I'm asking for the domain of that function, right? Okay, just make sure we're all clear on that. I want to know the domain of that function if I define it that way, which is equivalent to asking for what values of x does that power series converge. Now, let's get into that. How do we show series convergence and divergence? Well, look, the only thing that's really being affected here in the problem, in this expression, the only thing that's actually being changed is the value of n, right? X stays the same the whole time, right? For a fixed value of x, this thing's going to start adding up. So why don't I just treat this thing the way I did before when we just had numbers? And let's just see what happens to this part right here. Let's see what happens to this in here. Right? That's something we can work with, right? That's what we were doing in the previous sections. So watch what I'm doing here. I'm going to do a ratio test. Why am I going to do a ratio test? Because I got factorial in there and some powers. But I'm going to do a ratio test on everything in there, including the x. N goes to infinity, not 0. What does the ratio test tell me I need to do here? A sub n plus 1 over a sub n. So this entire thing is our a sub n. Plug in n plus 1, and what would you get? So right here, n plus 1, you get 2 times n plus 1, which would be 2n plus 2. But then it's 1, so 2n plus 3. 2n plus 3 is what I get when I plug n plus 1 in right there and distribute through and clean it up. Then I have to plug in n plus 1 up there. So I have x to the n plus 1 all over n plus 1 factorial. Is everyone clear that that's what I would get if I plugged in n plus 1 into the expression, into the sequence in there? All right, now I need to divide that by a sub n, which is the same as multiplying by its reciprocal. So the reciprocal of that is n factorial over 2n plus 1 times x to the n. Now, just as before, we can start messing with things like the n plus 1 on the x can be split apart, right? The n plus 1 factorial can be split apart. So I'll do that on my next step. How do I rewrite the n plus 1 factorial? N plus 1, and then times n factorial. Then over here, n factorial, and then 2n plus 1 times x to the n. I believe I'm going to get a lot of cancellation here. Yeah, my x to the n's cancel, and factorials cancel. And that's it. That's it. So let me just rewrite everything. Limit n goes to infinity. I've got 2n plus 3 on top with an x next to it, right? All over. You want to do it that way? 2n squared plus 3n plus 1. And that's it on the bottom, right? I'm glad you asked. Well, it is a constant, and we can't take it out, but we need to make sure we look at it as the absolute value of x. We can't take it out as just an x. It has to be absolute value. So here's what I would do instead. I'd write this way. I'm just going to put the absolute value of x next to it. What happens as n goes to infinity? Infinity over infinity, you do L'Hopital one time, and you get what? 2 over 4n, and then you do infinity on the bottom, but the top stays what? 2, so that should go to what? 0. So this goes to 0 times the absolute value of x, which is, so if I have a fixed x, right? If I fix my x, I'm going to multiply it by something that's getting infinitely small, which means this thing is going to go to 0, isn't it? Now, what does the ratio test require for convergence? What does the ratio test require for convergence? Because that's what we just ran, right? This has got to be less than 1. Is it? Therefore, what does that tell us? Therefore, by the ratio test, which I already stated above, I'm doing the ratio test. Therefore, this series converges, right? But what we were asking, remember, I said what we wanted to know was the values of x for which it converged, right? But because of the way this limit worked out, did it matter what x was? If I would have plugged in 10 here, it would have been squashed down to 0 with this, right? If I would have plugged in 1,000, it would have been squashed to 0. Because that's going to 0, right? So any value of x I would have picked would have worked. That means this thing converges for all x, for all real values of x. You could say that a couple of ways. From negative infinity to infinity, or you could say, you know, double struck capital R, which means all real numbers. So here's what we're getting at. If I go in here and I replace x with a number right now, I promise you this series is going to converge. And it doesn't matter what number I pick, all right? Doesn't matter. So to illustrate that, I have this. Here's the actual series. So what I've done is I've written a program I can't use 0. Let me see here. Okay, so here's what we got. Here's the series, right? That's the one we're interested in. And with the way I wrote this code out, I'm going to be able to pick the value of x that I want. And then I'm going to be able to have the computer add up the first however many terms. And these are the actual terms I'm going to add up. So if I plug in x equals 1 right now, okay, so if that's just a 1, then 1 to the n is 1, right? So this just becomes 2n plus 1 over n factorial. If we start at n equals 0, what would you get? 1 over 0 factorial, which is 1. So you just get 1, right? And then you say plus, now let n be 1. What would you get? 3 over 1. And then remember, x is there also, but I'm replacing x with 1. Yes? So what's 3 times 1 plus 1? 4. So you see it adds up to 4? Okay, what should happen now is that if I take more terms in the series, keep on adding more and more terms in the series, this nth partial sum should do what? Is it going to blow up or is it going to converge? It should converge. That's what we just said. We said that no matter what x I pick, this sum should converge. So now here come more terms. You see the terms? You see what's happening to this value? It's 8 now, 8.1, 8.15, 8.154. Look at, now I'm adding more terms. Is it changing? Slowly, right? Well, where did it change? Right around there, right? It was 8.15484, and look at how many terms I have in this series now. I've already got like 20 terms in the series. The further out I go, it's not really changing the value. Now, I had to have the computer around somewhere. But what's happening is that the further I go, right, the closer and closer I get to a number. Now, I'm not telling you what this number is, but I'm telling you it does converge. And I'm hoping I'm convincing you that the 8's going to stay the way it is now. The 1's going to stay, the 5's going to stay, the 4's going to stay, and the things that are changing are way out here, right? So the more terms I go, the more precise my answer is, but it's converging. Now, if I change my x value, is it going to change the fact that it converges? So let me change it to 3. So now I take the first two, they add up to be 10. So maybe you're thinking, all right, this thing's going to, blow up now. Well, according to what we proved, it should converge. And look at that, 140.599. Look, I'm there. I mean, I've gone that many terms. I think that's good enough for us to convince it's not blowing up. You see that? It's converged. Yes. No matter what my x value is, I'll just come in here and change the x value. Change it to negative 12. Look, if I change it to negative 12, now it's an alternating series, and it still is convergent. Look, 23,000. If I go out further, there it goes. Hold on, x negative 11. Uh-oh. That should converge. It's converging to something. That's a lot of terms. This could be a mistake in my code, but no, it looks like it's converging to 0. So those first few terms were kind of big, but it looks like this sum is converging to 0 because it's an alternating series, so some of them are taking away, right? But we have proven that regardless of x, it's going to converge. All right? Now, we'll study another one. We don't have enough time, but let me tell you what's going to happen. This is our next one. Just look at this for a second. There they are. How much time do we have? 5 minutes. Well, I guess I can just show you this one. I thought this was in our notes, is it? It's the next problem, right? Yeah. Okay, so look at this one right here. This is a different power series, right? This is a different power series. So look at right now. My x value, say is here. Let's see if it looks like it converges, all right? If I come here, does it look like it's converging? Look at that sum down there. Does that look like it's holding steady? Looks like it's converging? Okay. Let me try and take an x value out here. There we go. So this is a different x value. Now my x value is 1.85. Let's see if it converges. Uh-oh. Uh-oh. See it? Uh-oh. It's not converging. It's diverging. So there's some window here of x values where it converges and diverges. There's a window. In the previous problem, we saw that the window was everything, right? Everywhere it converged. And this problem looks like there's some sort of window where it's going to converge. And so what we'll get into next class, is that when it comes to series, look at your handout here. Look at the theorem on the second to last page. The theorem, you'll see it. It says, given a power series, you'll see that? There are three possibilities. One, it converges when x equals a only. Now, we already said that. If x is a, it adds up to be 0. So it either only does that, or it converges for all x, which we showed in that previous problem, or there is a number r such that when x, absolute value of x minus a is less than r, it converges. That means there's a window of convergence, which we call an interval of convergence. But for all power series, it's one of those three possibilities. It's either it only converges at x equals a, it converges everywhere, or it converges on an interval. And so that's what we set out to do from here on out with the power series. We were given a power series, we try and determine which of those three cases it is, and if it's an interval, we have to find the interval. Understand? We'll pick up with that next class. You've got plenty of homework to do out of that section, so get going with that. And as far as when is our test supposed to be, it's just not, I mean, there's just no way we can do a test. Don't you all agree? I mean, look, we're going to wind up having a third test the week after Thanksgiving. I mean, it's just going to have to be that. It's just going to have to be that way. It may even be the last day of class, which means you take an exam and then you come in and take a final. I don't know how we're going to do it, because we have two options. You come back from Thanksgiving, we take a test that day, or we try and do it the last day. I don't know what would be best. I mean, we only have how many more days? 3 classes. That's all we have left, 3 classes. Right? Class periods. Because we have next Tuesday only, right? Because next Thursday is Thanksgiving. We come back, we have Tuesday, Thursday, that's it. So, oh wait, we have this week too, yeah. Yeah, but we're supposed to cover Power Series, Taylor Series, Maclaurin Series. Yeah, we're going to spend most of our next class on Power Series. What do y'all think? I mean, do y'all want to have it? We could have a test next week on Tuesday on just convergence. Like I give you a series and I ask you if it converges or diverges. Yeah, just on the test on the sheet. A comprehensive quiz. I don't know when we'll find the time for that. Yeah, I mean, we're not going to go back and do like techniques of integration, you know. What do y'all think? I mean, it's your grade. Well, now it's just we're going to mess with the series. We're going to start, you know, this is a power series. Now we start seeing that we can represent functions that we've always worked with in our lives with power series, and start learning how to like multiply and divide power series and integrate and differentiate power series. And I mean, it's not like we're doing more tests or anything. We'll have to find the interval of convergence. Usually I like to put the interval convergence on the same test as the ratio or the other test because it's all the same thing. I'm not getting many votes. How many of you think you'd want to have a test a week from today on just convergence and divergence? Okay, how many of you are opposed to a test next Tuesday on just convergence and divergence? All right. So only 2 opposed. So what would be your what are some suggestions as far as what you think you would want to do? If we didn't do it on Tuesday, what would you? Extra test? Take home test. Of course everyone wants to take home test. Yeah. See, my thing about take home tests is that they're always tough to grade because they're always, you know, harder. So they're a lot of work. They're a lot of work for you and me. Over the Thanksgiving holiday, I'm not quite sure you really want to be doing convergence and divergence tests on series, you know? Yeah. Yeah. Okay, you think about it, I'll think about it. Let's make a decision on Thursday for sure what we want. But be doing your homework. I mean, the worst thing you could do right now is just be like, well, I'll figure it all out later, you know. Do your homework. Yeah, Thanksgiving, man, I'm going to just sit there, eat turkey, and do calculus. No, do your homework.